We'll begin a look at the blood today. We'll get an introduction into this tissue that we have. So blood itself, in a sense, the blood is designed to only be in two places, either in the blood vessels or in the heart. And so it pumps from the heart, moves into the arteries, and then goes out into smaller and smaller blood vessels until we hit the capillaries, at which point we're going to do one of our two processes of gas exchange. And so here we're going to drop off oxygen and pick up carbon dioxide based on some pressure gradients that we have there between the two. And that's going to allow us to exchange those gases there. And then the same process is going to continue once again, not in the tissues, but in the lungs, to allow us to drop off carbon dioxide and then pick up oxygen anew from the lungs. So blood circulation, as it's moving around, is going to be found in a couple of different places within the vessels themselves. And so when it gets to the capillaries themselves, as it moves from those arteries, it's going to get into the capillaries. In those capillaries, we're going to drop off oxygen, pick up carbon dioxide, pick up waste, things like that. It's going to head back towards the heart. And then from there, it's going to move to the lungs. In the lungs, it's then going to drop off the CO2 and pick up fresh oxygen. From there, goes back to the heart. And so it's essentially going from a process where we have kind of our little heart here, and then we head out from the heart into the arteries. We come into capillaries, and then we're going to come back in through veins. Those all converge back together. And then we come back into the heart again. And then from there, that blood's going to go back out to the lungs. There's our lungs, not drawn to scale or anything. So that blood goes out to the lungs themselves. And again, ends up into a capillary bed. And then we pick up that blood again. It's now oxygenated again. And then we come back into the heart. So this process is going to go around and round and round. And we're just simply dropping off nutrients, picking up waste in the tissues, and then dropping off carbon dioxide and picking up oxygen in the lungs. The blood that we do have, in terms of what we see there, does have different components to it. So we have some different things that we're going to find inside the blood itself. And so when you go and you give a blood sample, one of the things that they may do to the blood, depending upon the type of test that they need to run, is they're going to take that blood and put it into a centrifuge. As we put it into that centrifuge, it's then going to essentially divide the blood up based upon the density of the substances that we have. So take the blood out, put it into a centrifuge, spin it down, and then that blood is going to spin down into its different components based upon the densities that we have there. So the most dense portion is going to be the red blood cells. So we're going to have our erythrocytes, our red blood cells here at the bottom. We're then going to have another part of cells, which is termed the buffy coat. And this is going to be all of our white blood cells and our platelets. And then the last portion, which actually makes up generally the greatest quantity, is the plasma. And so this is essentially all of the water, plus all of the things that can be dissolved and floating in the water itself. And so the red blood cells, white blood cells, and platelets are referred to as our formed elements. These are the actual cells. These are the things that we actually form and put into it. Just like with other connective tissues, that is our living component. And then we have a non-living component, the plasma. So blood is a tissue for the body by definition. And so it is the only fluid tissue that we have. And it's basically combined of the non-living portion, the plasma, and the living portion, the formed elements. The formed elements come in three different types. We have our red blood cells, our white blood cells, and then the platelets. And so each of those are formed and placed into the bloodstream itself that's there. When we look at and see, in a sense, kind of how a person's blood is doing, one of the things that we're going to look at is to look at the amount of RBCs that we have there. And so when somebody asks for their hematocrit level, sometimes even just referred to in short as the crit, that's there, that term is essentially looking at what's the percentage of red blood cells in the total volume of the blood. So back to that centrifuge, when we have our test tube there, how much of that test tube was red blood cells, how much of it was plasma, and I'm just going to leave the middle there as a white in the center there for our Buffy coat. And so how much of that percentage did we have of just the red portion? Was it 45%? Was it 40%, etc.? And so what kind of a percentage of those red blood cells we actually have in that composition that's there? Other things that we can see when it comes to blood as far as its physical characteristics is blood, especially when it's just taken out of the body, is going to have a little bit of a sticky consistency to it. It is definitely opaque. We can't see through it because of all those cells that are in there. And because of the cells and all of the things that dissolved in the plasma, it will tend to have kind of a metallic taste to it, or kind of oftentimes an irony type of a taste to the blood itself, if you were to taste it. Depending upon where we get the blood from dictates what the blood in a sense looks like. When it is a bright red, a scarlet red, we have a oxygenated blood. When we have a dark red, I think I got the dark one here. Yeah, there we go. We have deoxygenated blood. So the scarlet type blood we're going to get from our arteries, and the darker blood we're going to get from our veins. That's there. And so typically if you've donated blood, what you've then seen was this darker blood there. In there. Perhaps if you work in a hospital setting, you may have seen a blood sample that was going to test for the blood gases, and so they may have taken an arterial sample that's there. Blood's pH is slightly on the basic side, so it does tend towards the basic side of the pH scale. So we're going to be slightly above 7 for that, but that's going to help us to buffer out any kind of acidic conditions that may be coming into it. Body temperature is normally 37 degrees centigrade. And here the blood tends to be on the warmer side. This is part of what allows the blood to help to warm us. So we can take that warmer core blood out towards the surface of the body and warm the body itself. We do have quite a bit of blood. Kind of on the average, we tend to say that the body has about 5 liters of blood, which accounts for about 8% of body weight. So for males, it tends towards the higher side. For females, it tends towards the lower side. So if you kind of take the average in between the high end and the low end on either of them, then we get that 5 liters in general for blood. Blood's main job is distribution. We're bringing that oxygen to the tissues. We're taking away the waste products from the tissues. We're delivering nutrients to the tissues. We're delivering oxygen to the tissues, picking up the carbon dioxide from the tissues. It's all about delivery in a sense. At the same time, it does have the ability to regulate. And so we can regulate different substances that may be in the blood, everything from carbon dioxide and oxygen levels to things like blood sugar levels, to ion levels in the blood itself, to pH, lots of different things that we can do there as well. And then we also have body protection. And so we have the ability to fend off potential substances that are coming into the body, antigens that shouldn't be there. So transportation, as I said, oxygen in, carbon dioxide out, get the nutrients to the tissues once they've been picked up from the digestive tract. So deliver them to where they need to be. Perhaps send some of those digestive tract nutrients over towards the liver, have the liver process those components that are there. Metabolic wastes, things that are being produced by all of our cells all the time, are going to potentially be helped to be eliminated here. Some of those may be actually eliminated through the breath, but the majority of them are going to end up over towards the kidneys. So we're going to deliver them to the kidneys and the lungs and allow us to get rid of some of those metabolic wastes that we have in the body themselves. It's going to transport, we just got done talking about the endocrine system, so our hormones. Without the blood for distribution, the hormones would take forever to get over into the tissues. So it would have to move through the tissues from one space to the next, and that would just take a huge amount of time. Next up, we have the regulation processes that are there. We talked a little bit about temperature, so having a higher temperature helps us to bring that warmer blood up towards the surface. But at the same time, we also have the ability to cool ourselves off. And so when we want to conserve energy, we're going to bring that blood deeper towards the core of the body. When we want to get rid of some of that heat, then we're going to bring the blood up towards the surface, do a little sweating at the same time, and we're able to eliminate some of the heat that has been put onto the body itself there. Regulating things like pH. So we said that the pH was slightly on the basic side. It also has the ability to buffer the blood. So we have some buffer systems within the blood as well, and we'll talk about those a little bit later on. The protective side of things comes in a two-pronged portion. I mentioned before that we have kind of the white blood cell side attacking anything that is not supposed to be in the body, so going after all of our foreign invaders that are there. They're going to do that through the formation of antibodies from our white blood cells. We've got other white blood cells that are going to directly attack them. So we've got our T cells, things like that. Our monocytes are going to go after them in terms of phagocytosis, etc. And then we also have, because the blood is meant to be only in the heart and the vessels, if one of those vessels becomes damaged and the vessel is broken, we're going to need to be able to essentially plug the hole. And this is going to occur by initiating a clot to be formed within the blood itself. And so we have things like platelets, one of our formed elements that we mentioned before. And then at the same time, the platelets are going to be kind of a physical barrier in a sense, but then we're also going to have to activate some plasma proteins. And so we're going to have to take some of these proteins that are normally in the blood, that are dissolved in the blood, are going to then have to be brought out of solution and allowed for us to make that clot to form inside the blood itself. But we'll talk about that later on. The plasma component is primarily water. And so we have a whole bunch of water and then a whole bunch of other things. Essentially anything that can end up in the blood from our food, from the air, from things we touch, etc., can end up inside the blood itself. So we have a large number of proteins. One of the biggest and one of the more important ones is albumin. From there we have things that are non-protein nitrogenous substances that may be there. These are all waste products. So we have things like lactic acid, urea, creatinine. Those are things that we're going to try and get rid of out of the body. We have our organic nutrients. So these are things like our carbs that we have in the body, our proteins as far as the amino acids once they've been broken down, those types of things. All of our electrolytes. And so all of our substances that are ions that are inside the blood as well. And then we have a little bit of the respiratory gases. Much more of the carbon dioxide is dissolved there rather than the oxygen. For these formed elements, we have the red blood cells, the white blood cells, and the platelets that are there. But when we actually look at the cells here in a little bit, we're going to see that the white blood cells are the only actual complete cells. They have a nucleus. And so they have everything that they need in order to do the function of kind of a normal looking cell. They have organelles inside them. They have the ability to manufacture things, etc. Red blood cells lack a nucleus and they don't have organelles. They're basically all just filled with hemoglobin. And we'll talk about that in a little bit. So there's not a whole lot going on inside those red blood cells other than carrying oxygen. And then the platelets, as we'll see, these are actually just kind of chunks of cells. They're cell fragments. And so these are just pieces of a cell called a megakaryocyte. And that megakaryocyte kind of allows pieces of it to come off similar to that of, say, think of a sebaceous gland. How a sebaceous gland kind of takes little pieces of itself off and sends it out of the cell. The cells themselves have a limited lifespan, and so they're only going to live for so long. So rather than dividing once they've been released out into the bloodstream, they're basically just going to be, in a sense, renewed or replaced by more cells in the bone marrow. So we're going to lose all of the cells that we formed, and then we're just going to break them down and recycle them, and then we can make new ones to replace them once they've died off. So here we have a blood smear, and this blood smear shows us the different types of cells that we can typically see. And just like we saw in that spun down blood sample, we've got lots of red blood cells, many red blood cells making up the majority of what we see here. And then we do have some of our white blood cells here as well. The white blood cells are fewer. There are much less of them. Some of them are in higher quantity, like neutrophils. So those are the ones that we see the most of in the blood itself. And then the next one up is lymphocytes in terms of numbers. And then monocytes are the next one in terms of numbers. And then not shown here on the slide are eosinophils and basophils as well. So we'll see those in even less numbers than those three. And then here we have a little cluster of platelets. And so those platelets are just those cell fragments, those cell pieces that we have floating around in the plasma as well. So we'll talk in depth here about the red blood cells themselves. So when we look at a red blood cell, it looks like a biconcave disc. I always kind of think of like a jelly donut in a sense that's been squeezed in the middle. And so it has, if we look at it on the side, it has this indentation on either side. So that's the biconcave component to the cells themselves. There's no nucleus inside. There's no real organelles inside. What it has is a huge amount of hemoglobin. And that hemoglobin takes up almost the entire inside of the cell. These cells need to be relatively flexible. They're going to go through blood vessels that are essentially smaller than they are. So they're going to have to be able to squeeze and fit into that blood vessel there. And so even though I drew it blue here, they're going to have to be able to kind of squeeze into that blood vessel to be able to get through. And they're able to do that because of a protein called spectrin. One of the more important ones there when it comes to the flexibility of the cells. This is what allows them to squeeze through these smaller blood vessels and make their way to wherever it is they need to go within the body itself. So here we see that biconcave disc again, a little bit better drawing than what I just did for those cells. It also most kind of reminds me of like an inner tube kind of a thing, whether it's for boating or sledding. You can kind of see that indentation there where you would sit in a sense. Red blood cells are designed to carry oxygen. And in order to do that, they need a huge amount of hemoglobin. So we have upwards of 97% of the inside of the cell contains hemoglobin when we get rid of the water component. There's an awful lot of water inside there, but in terms of anything that is not the cytoplasm, in terms of the things that are made inside the cell, almost all of it is hemoglobin inside there. That biconcave shape that we have there increases the surface area relative to the volume of the cell. If we had a sphere for a cell, we wouldn't have as much surface area. And so that surface area, no matter which way we look at that particular cell, is less than a cell of basically the same size that has that biconcave disc. More surface area means more gas exchange. And so we have the ability to manufacture or get that oxygen into the cells as much as possible. The cells carry oxygen, they're not going to consume oxygen. So if they need to make ATP, they're going to do this anaerobically. And so they're not going to use up any of the oxygen that is inside the cell there. Red blood cells' job is essentially 100% gas transport. And so we're going to transport the oxygen, we're going to transport the carbon dioxide, one in one direction, one in the other direction, oxygen going to the tissues, carbon dioxide going away from the tissues as we see it there. Hemoglobin itself very easily and quickly reversibly binds oxygen. So it has a reversible reaction that occurs there. For every one hemoglobin that we have, we get 4 oxygen molecules able to be bound to it on there. Hemoglobin itself, so that it can bind all 4 of those oxygens, is made up of 2 separate protein chains. We have 2 alphas and 2 betas. So altogether we have 4 proteins inside that hemoglobin, and each one is going to bind up an oxygen to it. At the very center of the hemoglobin itself, on the heme portion, we have an iron, and the iron is actually what's going to bind the oxygen. So that's what's going to bring that into the hemoglobin and bind it to that. Once we have that, we have what we call oxyhemoglobin, and that's what's going to allow us to transport all of that oxygen along the way. So here we have our 4 proteins, 2 betas, 2 alphas, and then an oxygen is going to come along here and bind to each one of the irons in the center. So it's going to be able to bind to that and allow for that transport of our 4 hemoglobin molecules at that time. As I mentioned, once we have hemoglobin bound to, or oxygen bound to the hemoglobin, we're going to call it oxyhemoglobin. So to denote that it has oxygen bound to it, we have the oxyhemoglobin. From there we have deoxyhemoglobin. So once the oxygen is gone from the hemoglobin, so there's nothing on it, there's nothing else bound to it, it is going to be deoxyhemoglobin. And then lastly, when we bind some of our carbon dioxide to the hemoglobin, we're going to get what we call carbaminohemoglobin. Say that a few times in a row and see how well your tongue gets all twisted. So a small component of the carbon dioxide is going to be bound to that hemoglobin as well to carry it back towards the lungs from the tissues. Red blood cell production is on a constant basis. And so the red blood cells themselves are constantly being produced. And as they are, we call this hematopoiesis or hemopoiesis for the term to say that we have blood cell formation. If you remember back to talking about bones, you know that the bones have red bone marrow in them. And in that red bone marrow, we are making blood cells. And so this is found in different places within the body, some in the axial skeleton, some in the appendicular skeleton. That's there, so it's going to be found in like the hip bones, the skull, and then in the ends of our long bones, we're going to find it in places like the femur and the humerus, found at the ends of those bones in the epiphyses, where we have still red bone marrow there as well. The blood cells themselves are going to develop from a stem cell. In the case of our red blood cells, this is going to be the hemocytoblast. And that hemocytoblast then differentiates into what we call a pro-erythroblast. And now this cell is essentially committed to becoming a red blood cell. So its fate is determined, so to speak. From there, they continue to develop, and now they're essentially starting to manufacture the things that the cell is going to need. It's going to grow, things like that. And our pro-erythroblast is going to become what we call an early erythroblast. And so it's going to go through a process where we've got to develop the things inside the cells in order to manufacture. So we're going to need lots of ribosomes. Those ribosomes are going to give rise to the production of hemoglobin. And that hemoglobin, once we see a large amount of that, we now have what we call a late erythroblast. The early erythroblast was when we were manufacturing the ribosomes to be able to make the proteins. And then from there we have our last phase, where we're going into a normal blast into what we call a reticulocyte, the nucleus is going to become ejected from the cell. And so it's essentially going to kind of spit out that nucleus. And in the process, we end up with that biconcave appearance within the cell itself. The reticulocytes now are immature cells, and those reticulocytes are then going to mature further into the erythrocyte that we have there. And so we can see that progression of the cell itself as it continues to move along until we have our now fully formed and functional erythrocyte, and this can then start to transport oxygen and carbon dioxide in the blood for us. The production of red blood cells is designed so that it basically keeps up with what we have lost. And so the number of cells that are dying are replaced by the number of cells that are being manufactured. In this way, the number remains relatively constant. And so this is going to keep us in that kind of general area where the numbers go down a little bit and then they come back up a little bit. And they're always kind of just fluctuating just a little bit in terms of those numbers from our set point. And so they go down a little bit, they go up a little bit, and that's it. This makes it so that the tissues aren't going to become hypoxic. So if we have not enough red blood cells, if our ability to carry oxygen is diminished, our tissues are going to become hypoxic. If we get too many cells, though, so if we start to manufacture those cells and just the numbers go up and up and up, then we're going to start to crowd the blood, and that's going to change our viscosity. The viscosity is going to go up, it's going to make the blood thicker, and it's going to be harder for it to flow. But the production of those red blood cells is all dependent upon having the building blocks to make those red blood cells. We've got to have the raw materials. And so we need things like iron. So it's got to be there for the hemoglobin that we're producing. We need amino acids to make the proteins that are involved with the cell itself. And then we also need adequate amounts of B vitamins. Take any one of those out and we're going to become anemic. We're going to not have the right kinds of red blood cells being produced. So as our body is going through its kind of day, we're monitoring how well the tissues are oxygenated. And so when we have a hypoxic situation, that's going to trigger the release of a hormone called erythropoietin. And so erythropoietin is one of the hormones that does get released by the kidneys. And we'll talk about this when we get into the urinary system a little bit more. This is what's going to trigger the production of more red cell production. So it could be that we've got less red blood cells. It could be that there's less oxygen available. So this may be a lung issue. This may be a atmospheric issue that's there. And so we maybe have gone up into the mountains somewhere, we're at elevation, and now we need more oxygen carrying capabilities because there's just not as much there in the air itself that's there. We may be putting more demand on it from our tissues in general. If erythropoietin is released, this is going to increase the numbers of red blood cells that we have, and that's going to increase the numbers that are now circulating in the blood itself. And so now our hematocrit is going to start to rise. So a person's hematocrit may have been down at 40, and we need to get it back up towards 45. And so those levels now start to rise. And the process itself is just a negative feedback loop as far as the production of those red blood cells. In some way or another, we've got reduced amounts of oxygen carrying capability or oxygen coming to the tissues themselves. This gets sensed by the kidneys. Kidneys release erythropoietin, stimulates the red bone marrow. Draw some red bone marrow in there at the end of the femur here. And so that red bone marrow starts the increased production. That leads to more red blood cells as long as we have all the building blocks that we need. And that then allows for more oxygen out in the blood. And then our tissues start to do well again. So we said that it requires the components of kind of diet in order to manufacture normal red blood cells. So we need adequate amounts of proteins so that we can get the amino acids that we need. We need energy in general, so we're going to need carbohydrates that are there. Cells have phospholipid membranes, so we're going to need some lipids in terms of that. We're going to need cholesterol in order to make those plasma membranes as well. We're going to need iron. So although we can recycle the majority of the iron that we have within the body and keep it, we do lose some iron at times. So we may need to replace that. One of the big B vitamins that we need is B12. We'll talk about this more when we get into the digestive system as well. And so if we're lacking vitamin B12 and the ability to absorb it, then we're going to end up with a pernicious type of anemia. That's there. So iron is normally stored in the liver. So iron is there. It's also in the hemoglobin within the body itself. And so 65% of it is in the red blood cells, but we're going to store some of it in the liver, and we're going to store some of it, and part of it's being broken down inside the spleen. Those that come from the liver and the spleen are going to head towards the bone marrow for more production that is there. A certain amount of that iron, once it's broken down from red blood cells, is going to be stored away, and as they're going to be bound up to a protein, and we're going to have them known as either ferritin or hemosiderin. And these are our protein-bound components of iron itself. When we're transporting the iron from, say, the liver to the bone marrow or wherever it happens to be, it also needs to be bound to a protein so that we don't lose it as well, and that gets bound to a protein called transferrin. And so kind of think of it as transferring the iron. That's going to allow us to transfer it to the next place that's there. Red blood cells themselves are the longest living of our formed elements in the blood. That being said, they still have a relatively short lifespan. And so we're looking at something in the neighborhood of 120 days at the most there, and that 120 days then equates to roughly 4 months. So the average lifespan of a particular red blood cell could be 120 days. Some of them are going to be a little bit more, some of them are going to be a little bit less, depending upon kind of what happens to them. Their cells don't have a nucleus. They basically don't have any organelles. So as they age, the cells become more rigid and fragile. Now, as they're starting to go through those blood vessels that are small, our red blood cells can't bend as much. They have a hard time getting through those smaller capillaries that we have. And so when that happens, they may even, because of the fragility, they may break. That's there. So they don't have any way to repair things. The hemoglobin isn't as functional anymore. It starts to degrade in there. We can't make any more of it. We can't alter it or anything like that. So they have a relatively short usefulness for the cells themselves. Those cells that are no longer functional are going to be destroyed by macrophages, primarily in the spleen. And in that spleen, then that's going to essentially break the hemoglobin down into its components. We're going to have heme, we're going to have globin, and we're going to have iron. And so we're going to take all of those three components out. Some of it is going to be recycled and reused. Some of it is going to be disposed of. And so the heme and the globin portion, in terms of the hemoglobin, are going to be broken apart. And the heme component is going to become a waste product. And so this is going to become something that we need to get rid of. And so heme gets broken down into bilirubin. Bilirubin then goes over to the liver. And when the liver creates bile, that bilirubin is going to end up in the bile itself. And so it has kind of a yellowish pigment, and it adds to kind of the yellowish green color that we have for bilirubin itself. Once it's released into the intestines when we have fats in our diet, some of the bilirubin gets converted into urobilinogen, that is there. Some of the bilirubin is going to be converted into stercobilin. Stercobilin is going to be a component that gets lost in the feces. Again, this is going to create some of the coloring to the fecal matter itself as well within the body. The urobilinogen portion is then going to head over to the kidneys, and we're going to get rid of more of that bilirubin there. If we don't get rid of that bilirubin, then we're going to end up being jaundiced. It's going to build up in our bloodstream, and that is not a good thing. Again, we'll talk about that a little bit more when we get into the digestive system as far as how that goes. From there, we have the globin component. This is now our protein. This is going to get broken down into amino acids, and then those amino acids are going to go into the blood, and they're going to go wherever they need to go. Whatever body part, in a sense, needs that particular amino acid, it's going to take it up into it. It could become another red blood cell. It could become something else as well. As that cell is being destroyed, some of the hemoglobin is released into the blood itself and is going to get phagocytized as well. And so it's going to be bound up to another protein called haptoglobin, and then the phagocytes are going to then destroy it from there. So here's kind of a schematic drawing of what's happening to those red blood cells as they're getting broken down. So here we have a macrophage. This is primarily in the spleen, but it could be in the liver or even the bone marrow itself that it's there. We're going to break them down into our three components. We have our globin, we have our heme, and we have our bilirubin component that the heme is going to get converted into. And so it gets converted into bilirubin from biliverdin. That bilirubin goes over to the liver, and from there it's going to get released as bile into the small intestines. Get green here. And so it comes out there and goes into the intestines. A large majority of it is going to get released as stercobilin. Some of it does get reabsorbed as urobilinogen, and then that's going to go over the kidneys and get lost through the urine as well. And so that'll get converted into urobilin, and then it'll be ejected out of the body as urine at that point there. The last component that we had for the blood is the iron. The iron is going to primarily go to places like the liver for storage if we don't really need it at that point, or it's going to make its way over to the bone marrow for the production of more red blood cells. Amino acids are going anywhere that we need proteins to be synthesized. They can be utilized for that purpose. Different picture, same process. I won't go through this one here. So when red blood cells aren't formed properly, then we generally end up with some sort of anemia. We can also have anemias because of other things that are causing us to not have red blood cells available that are there. And we'll talk about some different components that are there. But essentially, the blood has low oxygen carrying capacity. And so this is where oftentimes the hematocrit is going to be then lowered in some way. Or perhaps the hemoglobin levels are going to be lowered depending upon what's going on in the person themselves. Either way, the blood oxygen levels that the person has can't support normal metabolism. So their body's going to be always kind of short on oxygen, which we may or may not necessarily see in as any of the symptoms that we have here: fatigue, paleness, shortness of the breath, chills, cold all the time, things like that. So some of the anemias that we may get are, in a sense, kind of no fault of our own per se. We can have hemorrhagic anemias. This is going to be loss of blood. And so oftentimes this is acute loss of blood, but it could also be chronic, something like an ulcer that's bleeding somewhere, something like that. We could have hemolytic anemia. This is where red blood cells have been destroyed too early, so they've ruptured. This may be a newborn issue. This may be a blood transfusion issue, things like that. We can also have aplastic anemia. Aplastic anemia basically means that the red blood cells aren't being produced. We've got something going on in the red bone marrow itself that is causing those red blood cells to not be able to be formed. Other things that are more potentially on a dietary type of an issue, we have things like iron deficiency anemia, or IDA. This is going to be caused by, as I said, potentially a dietary issue, so inadequate intake of iron. But at the same time, if we've lost a whole lot of blood, if we've hemorrhaged somewhere, and we've lost a whole lot of blood, that means that we've lost all the iron that we had. And all that iron is now gone. And so effectively, the person's going to need extra iron in order to make those new red blood cells come back. The digestive tract could be the culprit as well, in that they're not getting good absorption of the iron either. Speaking of lack of absorption, we have pernicious anemia. So I mentioned pernicious anemia in relationship to vitamin B12 before. Vitamin B12 is necessary for the production of normal red blood cells. And in terms of that, as we age, one of the things that kind of declines in our stomach production is a substance called intrinsic factor. Intrinsic factor is needed in order for us to be able to absorb B12. If we don't have enough intrinsic factor, we're not going to get B12 absorption. So you can't just go and give them a supplement of B12 because they're not absorbing it. So they can't eat it. So they're going to have to either get it into the blood directly or through an IM injection of B12. Other types of things can be genetic, and so sickle cell anemia and thalassemia, both genetic disorders that cause red blood cells to be formed abnormally. So sickle cell anemia causes the red blood cells to have a sickle shape. The hemoglobin itself is slightly altered into what we call a hemoglobin S, or a sickled hemoglobin that is there, and this does not carry oxygen as well as it normally should. Thalassemias are sort of similar in terms of the fact that they're a genetic component. Sickle cell anemia is typically those of African descent. Thalassemias are those more of a Mediterranean descent as far as their genetic past is concerned. With thalassemias, though, the cells themselves are more delicate. And so they're able to potentially become damaged and die. They also have a decreased amount of hemoglobin. Thalassemias come and sickle cell come in different varieties depending upon kind of the severity of the disease itself. And so here we have for sickle cell, we have a variation in the cells. We have a normal red blood cell up at the top, and then we have a sickled cell down at the bottom. And what this comes down to is just a single amino acid. And so one single amino acid has been changed in the genetic code, and that causes the change in the proteins that are then formed. And so we get a difference in the hemoglobin, and so we have a change in that protein that is there. And that leads to the sickling of the cells themselves. And then they start to get caught in places within the body, you get joint pain and oxygen problems within the body as well. So those were all basically problems with production. As far as lack of production, we also have things like polycythemia. And so polycythemia is where we have excess amounts of red blood cells. This one's going to be more on the rarer side of things, but it can be from things that are a little bit more nefarious, like polycythemia vera, where we've got a bone marrow cancer that is causing the crowding of the bone marrow itself. We can have a relative or a secondary polycythemia due to things like high altitude. So somebody who lives up in the mountains, especially if they were to come down and say go from the Colorado area and come to the Chicago area. In the Chicago area, you're going to be almost at sea level. You're going to be much lower. And if they go and get their blood drawn, they're going to look like they have excess amounts of red blood cells because they've developed them in order to carry more oxygen in the thin amount of oxygen that's in the air normally. One of the other ways is through what's called blood doping. And so this would be getting a blood transfusion when you don't really need one. And so this blood doping is typically just for athletes. And so an athlete just before their competition would give themselves their own blood back. And so typically 30 days or so before their competition, they take some blood out of themselves. And then just at their competition, they're going to then transfuse that blood back into them. So now they have a whole bunch of more red blood cells that they didn't have before. And so they're going to have more oxygen carrying capability, better ability to essentially have more endurance. And then from here, next time we'll talk about the white blood cells.